so the way that the questions are set will be slightly different. Alright, and we will go through 16 first. Okay, 16, 15, and 14 because 16 is being the most relevant. And what we are going to do today is we'll go through those questions that are pertaining to part 1. Okay, that means vectors, electric field, magnetic field. Okay, next week, okay, we will do the same 3 exam paper again, but we will do questions pertaining to part 2, the propagation of lossy medium, lossless medium, transmission, reflection, and transmission line. Okay, then it will be much better because then your memory will be very fresh. Okay, for your CA2. Alright, now you know the layout of the exam paper. Okay, there are section A and section B. Section A contains 5 small questions. You need to answer them. Okay, compulsory. 5 small questions. And section B consists of 4 questions. You need to pick any 2. Okay, you need to pick any 2 so that you are able to focus on the topic which you are more familiar with and you are more proficient at. But at the same time, okay, you need to know some basic about everything. Okay, that's the reason why part 1 is mandatory. Okay, as you can see from here, the constants are given. Okay, the symbols are also given. Alright, the symbols are also given. Okay, and the formula sheets are given. Alright, now get yourselves familiar with the formula sheets. Okay. Okay, let's start with the questions. Question 1, the electric field E in free space is given by E is equal to 2xx plus y squared y plus z. Find the associated free charge density rho in coulomb per meters cubed at the point P121 where the coordinate x, y, z are given. Alright, so E is equal to 2x plus y squared y plus z. Okay, you are asked to find the free charge density rho. Now, how to find the free charge density rho? Anybody has any idea? Anybody has any idea? At the point P Y
do curve of
Y. Any idea?
E do curve.
No curve. E never curve. E is only divergence. E never curve. Okay, curve is only for H. Okay, for the Maxwell equation where you have curve. Now remember your Gauss law. Okay, actually the equations I have derived in the class for you already, and this is equal to, this side is equal to rho dV over epsilon, and this side, what is this side? What is this side? What is this side is equal to? Remember, this is your divergence theorems. Okay, so what you get is actually, this equation is actually being derived in the lecture note for you already. Divergence of E is equal to rho over epsilon. You look at your lecture notes, it is in there. Alright, so what you have to do is to find the divergence of E at that point. Okay, then it will give you the charge density. So how to find the divergence of E? What is divergence of E? Divergence of E is equal to del Ex plus del Ey del Y plus del Ez del Z. Okay? If you look at the divergence, divergence of a vector is equal to del Ax, del X, del Ay, del Az, del Z. The formula is over here. Alright? do that. Del Ex del X, differentiate 2x with respect to x, give you what? 2, right? Differentiate Ey with respect to y, y squared becomes 2y, right? Differentiate 1 with respect to z, give you 0. So this is 2 plus 2y. This is your charge density over epsilon. Right? At the point 1, 2, 1. 1, 2, 1 means what? Y equal to 2, so 2 plus 2 times 2 equal to 6. Right? So 2 plus 2 times 2 equal to 6, which is equal to rho epsilon. So what is the answer? The answer is 6 epsilon naught. Right? Okay? Any questions? One more time. Alright. The equation's divergence of E is equal to charge density over epsilon is already given in the lecture notes. Alright? Divergence of E is equal to charge density over epsilon naught is given in the lecture notes. So all you have to do is find the divergence of E. You find the divergence of E from the formula is del Ex del X plus del Ey del Y plus del Ez del Z. Differentiate 2x with respect to x, give you 2. Differentiate y squared with respect to y, give you 2y. Differentiate 1 with respect to z, give you 0. So the answer is 2 plus 2y equal to rho over epsilon. Now at the point 1, 2, 1, at the point 1, 2, 1, that means y equal to 2. So 2 plus 2 times 2 equal to 6. So rho is equal to 6 epsilon or 6 epsilon naught. So the answer is D. Alright? Everybody okay? Okay, yeah? Okay. 4-point charge of Q1 equal to 1 times 10 to the power minus 5 coulombs, Q2 1 times 10 to the power minus 5 coulombs, Q3 or Q4 located in space with the Cartesian coordinate 1, 1, 0, minus 1, 0, minus 1, minus 1, 0, minus 1, minus 1, 0. Now, you can look at it here. The 4 coordinates, every one of them behind the z is always 0. So that means it is on the xy plane, right? All the z's are 0, 0, 0, 0. So that means it's on the xy plane. That means it is here. One, 1, 0, x, y, p, which is 1, 1, 0. P1 is 1, 1, 0. P2 is equal to minus 1, 1, 0. So it's here. P2 minus 1, 1, 0. P3 is minus 1, 0. And P4 is here. 1, minus 1, 0. Okay, so it's actually the 4 corners of a square. The origin Q is 0, 0, 0, or we have the matrix. Find the electric field at the origins O. Q1, Q2, Q3, Q4. Now, what is the electric field at the origin O? Are they all positive charges? No, they are not all positive charges. Now, these are the 4 corners of a rectangle. 1, 1, minus 1, minus 1, minus 1, 1, minus 1. Okay, Q1 is positive, Q2 is positive, Q3 is negative and Q4 is negative. Okay, if that is the case, electric field come out from a positive charge and terminate on a negative charge, right? So electric field will be pointing this way. This is a positive charge. This is a positive charge will be pointing this way. This is a negative charge will be pointing this way. This is a negative charge will be pointing this way. Right? Okay? Everybody alright? Alright, huh? Okay. So now, what is Q1? Q1 is 1, 1 minus 1, 1. Okay, so 1 times 10 to the power minus 5. This is 1 times 10 to the power minus 5. This is minus 1 times 10 to the power minus 5. This is minus 1 times 10 to the power minus 5. Now, what is the total charge? Total electric field at the origin? Can somebody tell me? 0, yeah. Because it just cancels off, because you see, it's the same. So this one is double strength. You see, this is single strength, this is another one, this is another one, double strength. So they both cancel out. If you draw up the diagram, you can see that the value is just equal to 0. This is very similar to the one in CA1, the magnetic field. Okay, very similar to magnetic field, up and down, and then just cancel off. Okay, can everybody see that the total electric field is equal to 0? Okay, because the charge is the same, so this direction and that direction cancel out. So you see, so now you 5 marks, you get 10 marks already in the exam. Hey, quite easy, huh? Let me lock it. Okay, question 2. Explain the various components. Wow, that one is very easy, right? This one is very easy. What are the various components? Well, surface law, B is equal to mu naught I 4 pi ds prime cross AR double prime R double prime squared. What are the various components? B is the magnetic field, magnetic flux density. You could refer to your lecture notes. Mu naught is the free space permeability. Current, I is the current flowing, okay, on the conductor. 4 pi is of course just a constant. What is ds prime? ds prime is the elementary length vector along the current path. Okay, this is where the current is flowing. And what is AR double prime and R double prime? R double prime is the distance from the ds prime to where the observation point P is supposed to be. Okay, what is AR double prime tag? This is a unit vector, okay, along the directions from ds prime to P. Alright, so there is another easy 3 marks. Okay, just talk only, right? As long as you understand what is this equation is all about. If you don't even know what they are all about, how can you apply? Okay, you are expected to know what they are, alright? So before you can apply. Okay. Find the mutual inductance between a long straight wire and a square loop as shown. A student reasoned that since the mutual inductance M equal to phi over I, where I is the originating current and phi is the flux linkage, he should use the following process. Assume the current flowing in the square loop. Use separate laws to find the magnetic flux density produced by this current I naught. find the flux linkage from the square loop to the long straight wire, find mutual inductance. Comment on the process, explain why it's not a good idea, suggest an alternate approach, just indicate the process. Okay, that is also talk only. Alright? I believe that all of you know how to talk. Okay, otherwise you would come to here already. Right? You would have gone somewhere else. Okay, what it means is that to find the mutual inductance, a student assumes, okay, assume a current I flowing in the loops, okay, and then use the Barrett-Savage law to find the magnetic flux density produced by these current loops, and then integrate flux linkage, and then find the mutual inductance. Why is it not a good idea? Actually, I've said that in class already. The reason it's not a good idea is obviously Barrett-Savage law is it's not easy to apply. You want to apply Barrett-Savage law coming from this straight wire, this straight wire, this straight wire, this straight wire. You have to do the process 4 times to find the, and then you sum up the magnetic flux density in space. You do this 4 things. You can do it 4 times, and then you've got to find the vector sum of the 4 components. Then after that, you have to integrate from minus infinity to infinity. Wow, that is hell of a lot of difficult. Okay, so it is never a good idea. The good idea should be, you assume a current I flowing here, and you can use Ampere's law. Use your Ampere's law to find the magnetic flux density, which is very easy. Ampere's law magnetic flux density, V is just equal to mu naught I over 2 pi r. Alright, so it's a simple Ampere's law. Why must you use Barrett-Savage law 4 times if you can use only Ampere's law 1 time? And for the magnetic flux density, linking the square loop, just integrate over the square loop, and that is straightforward. Alright? So you can see that another 10 marks just by talking. Okay, why is it not a good idea? Okay, why is it not a good idea? Why is it? What is a better idea? 10 marks. So okay, do we have 20 marks already?
So can you roughly repeat the part?
Which part?
The front part again. The Barrett-Savage part.
Now, Barrett-Savage law, you can see here, it's not easy to use, right? Barrett-Savage law is not easy to use. Okay, and because this is not a continuous, it is one line, you use Barrett-Savage law 1. But there are 4 lines, you have to use Barrett-Savage law 4 times. Okay, now if Barrett-Savage law 4 times, you find the magnetic field flux density at the point here, then you find 4 times, then you have to sum up the 4 components. Now, you're going to use Barrett-Savage law 4 times, you've got to sum up the 4 components. How troublesome it is. And then after that, you have to integrate this magnetic flux density times the elementary area, integrate from infinity to infinity to find the flux linkage. Troublesome, right? But you use Ampere's law, you need to use only Ampere's law. If you assume the current along the long straight wire, you need to use Ampere's law. Ampere's law is easy to apply, so easy. Alright, so easy. And compare with Barrett-Savage law, obviously, right? You compare these two, which is easy? Okay. No brain, right? No brain. The answer is no brain. Okay, this one. Then after that, you get the magnetic flux density here. You get the elementary area and integrate over a small loop and not infinity to infinity. And that is much, much easier. Alright? Any questions?
So if you use the Ampere's law, right, against 2 pi r, right, the r is distance from the long wire to which part is correct?
Tell me.
Center.
Tell me. Tell me.
Yeah.
Tell me. Want to find the B at this point. What is your R? The nearest.
Yeah. So I say it's to the...
If you want to find this one, If it this one, the nearest.
Okay.
You don't go and do the origins, huh? Are you the one in GA giving me the origins?
Yeah.
Yeah. The magnetic flux density here is from here to here and not from the origins, huh? Okay, the R is not, there is no origin, there's an infinite line. This is the shortest distance, perpendicular to it. So at any point you want to find the magnetic field, this is the R. Okay, the perpendicular, shortest perpendicular
In the
distance.
center of the square, right?
Center what?
Center of the square.
Oh no. Any point in the square, because you see, down here the magnetic field and the magnetic field down here not the same. If you find the center of the square, it is 2 pi r. Remember 2 pi r. So you can got to find anywhere and then you integrate over the elementary area because at a different point, it's a different r, you see, correct? Not different r, so it's different. You cannot just find at the center and then multiply by area. It is not a constant. It is not a constant. This is a tutorial problem. Alright. What is a magnetic flux linkage? You cannot find, if let's say this is 2, 2, you cannot find the magnetic flux at the center here, and then the flux, you cannot find the flux density there, and then flux is equal to B times 4, or 2 squared, or let's say 2, 3, let's say, B times 2 times 3. This is wrong. Alright? Because the B is not a constant. If it's not constant over here, you cannot multiply. You can multiply by area only when it is constant. If it's not constant, then what do you do? Then is flux will be equal to B times dx dy and integrate over xy over the loop. Because it is, once it's not constant, you cannot multiply by the area. And the reason why, you see, Gauss law and all this, every time we just multiply by area because it is a constant. Okay, only when it's constant, then you can multiply by the area. This is a tutorial problem, huh? Okay, we have gone through that tutorial problem before. Alright, any other comments, questions? The magnetic field of a plane wave propagating in a medium is given by this. Medium characterized by epsilon I equal to 49, mu I equal to 4, sigma equal to 4. Determine the attenuation constant. Now, this one is very straightforward and very simple. The only thing is that you must know how to use which formula. Okay, I assume that you have the formula for good conductor, good dielectric, general, everything inside your cheat sheets already. So the important thing is find this one. And once again, this is equal to sigma omega epsilon naught epsilon r. Alright, this epsilon means epsilon naught epsilon r. Okay, we have seen many different variations. Epsilon equal to epsilon without epsilon r. Epsilon equal to epsilon r without epsilon naught. Omega is equal to f without the 2 pi. Okay, I mean, don't laugh. I assume that it's exam pressure, kanjiong or something like that, but this kind of mistake people make. Okay, remember this is sigma over omega epsilon, this omega epsilon naught epsilon r. Omega is a 2 pi f, epsilon naught and epsilon r. Okay, you must have all this, otherwise it's wrong. Okay, so once you got that, okay, you can use appropriate formula. But at this point here, first of all, I want to ask you, they give you sigma, they give you mu r, they give you epsilon r, they never give you omega. Where is omega? Omega is here. Omega is here. Omega is 10 to the power of 9 pi. Okay, omega is here. Okay, so you could go in here and to find whether it's very much greater than 1 or very much smaller than 1, or not much greater than 1, then you use the appropriate formula to find the alpha, beta, and zeta. Alright, that one I don't have to tell you how to do it. And be careful that this mu r is equal to 4. This mu I not equal to 1. A lot of time mu I equal to 1. Okay, this mu I equal to 4. But never mind, just substitute mu I equal to 4. No big difference. Okay? A plane wave traveling in air is normally incident upon a second medium if epsilon r2 equal to 4. Okay? So now I have this one, epsilon r equal to 1, epsilon r equal to 4, like this. Okay, if the electric field intensity of the incident field is given like this, find the phasor form of the reflected magnetic field. Well, again, it's very simple. Hey, why am I going through this? I thought this one we're going to leave it until next week. Next week. Oh, sorry. We skip. C and D we skip. Okay, next week then say. Okay. Because this week I think we focus on the electric field and magnetic field. Alright, this one will leave it until next week. Alright. As shown in figure Q2, a sphere of radius A is placed concentrically inside a metallic spherical shell. Okay, this one metallic. So this is metal. But this one they never say it's metal. The sphere of radius A, they never say it's metal. Alright? But this one they say it's metal. So read your questions carefully. Okay, consider the following two cases. If the sphere contains a volume charge density, okay, there's a volume charge density, and the outer surface of the spherical shell is grounded, find the electric field in the following region: R greater than A, smaller than B, and R greater than C. Okay. A, B, C. Now, so this one has a charge density. This one is a metal and it is grounded. What does it mean when it is grounded? Grounded means that outside here got no charge. Alright, so now the negative charges are here. Because there's a positive charge inside here, there's negative charge inside here, neutralized. Alright. Okay, and they are asked to find the electric field. There's no R smaller than A. Yeah? You see, this one is much easier, but not much easier. So when asked, there's no R smaller than A, so when you do this, okay, R greater than A, smaller than B. R greater than A, smaller than B. Now remember our E dot dA is equal to Q over epsilon. Gauss law, always look at symmetry. Well, this is symmetric enough. Remember the rho v inside here, the rho v is only a function of R. Rho v or rho v is only a function of R. It's not a function of theta, it's not a function of phi. If they are theta and phi, it's not interceivable, so don't worry. Always not function. If that's the case, now the electric field is equal to 4 pi r squared dr. It can just multiply by the surface area because it is constant. So the electric field will be dr, the radius r, electric field will be radially outward. Okay, because of symmetry, electric field radially outward, and at the same distance r, the electric field is constant. Okay, electric field is radially outward, and electric field is only PR is only a function of R, and at the same R, it is constant, and because this is constant, it can multiply by the surface area 4 pi squared R. Now, what is the charge enclosed? The charge enclosed, there is no charge here, but there is charge here. So the charge enclosed is inside here. Now, what is the total charge enclosed here? The total charge enclosed Q is equal to what? Charge density 4R. Is it 4R? 4R. Okay, I don't want to do all the shells, all these things. I just want you to go to the basic fundamental. Okay, the basic fundamental. What is the elementary volume? R squared sine theta d theta d phi dr. Is it R squared? Yeah, R squared, huh? Okay, so if that's the case, now it's become what? 4R cubed sine theta d theta d phi dr. I don't like this one. They don't have a big enough font. Okay, so how to do this integration? It's very simple, right? R cubed sine theta d theta d phi dr, which is equal to R cubed dr integrating from 0 to A, because the Gaussian surface encloses the entire inner sphere. Sine theta d theta integrating theta from 0 to pi. D phi integrating from 0 to 2 pi. So this is equal to R to the power 4 divided by 4, 0 to A. Integrating sine theta is what? Cos theta, right? Cos theta 0 to pi. Integrating phi is just phi 0 to 2 pi. So this is equal to A to the power 4 divided by 4. Cosine theta, cosine pi is equal to -1, right? Cosine pi is equal to what? -1, huh? -1, -2, Hey, how come? How come I got a sign wrong?
So you're not supposed to over 4 because it's 4R.
Sorry?
4R cubed. So you're...
4R cubed, okay. So the 4 is missing, thank you. 4R cubed. Okay, the 4 is missing. No, I'm not worried about the sign. This is cosine. Cosine pi minus cosine theta, right? This is equal to 2 or minus 2? Minus 2. Oh, minus cosine. Okay, thank you very much. No wonder I have minus sign is wrong. So this is equal to 2. And this is equal to 2 pi. So this is equal to 4 pi A to the power 4. Alright. So this is now what we have is we have 4 pi r squared ER is equal to 4 pi A to the power 4. So ER is equal to A to the power 4 divided by r squared. That's all. Okay? So this is when this is for R greater than A smaller than B.
What's the shortcut method?
Don't do shortcut method. I don't want to do. Because I don't want to confuse people. Now exam time already, yeah? Okay. Now, what happened for R greater than C? R greater than C, I draw a Gaussian surface here. Where is R greater than C? Now, Gauss' law, left hand side still the same, equal to 4 pi R squared ER. But what is the total charge enclosed? The total charge enclosed is 0, alright? Because if this guy got so much charge, that means there are so much electric field coming out. Now, each electric field must be terminated by a negative charge. So, one positive charge, one negative charge. Monogamy, no polygamy over here. One here positive, one negative. So, if that's the case, if the thing is not grounded, that means there will be same amount of positive charge outside here. But if it's grounded, that means the positive charge is drained to the ground. So that if you draw a Gaussian surface outside, the total charge enclosed is 0. Okay, if the total charge enclosed is 0, this side is 0. So ER equal to 0 for R greater than C. Alright, for R greater than C, the electric field is equal to 0. Alright? Any questions? Question 2. If the inner sphere is also metallic and radius A equal to 1 meter and spherical shell inner radius B equal to 2 meter, determine the capacitance between the sphere and the spherical shell. Now, both are metal. So this is metal. Metal. How to find the capacity? How to do that? I thought this all they have done in lecture. No. No. Okay. If this is metal, this is metal. Now, how to deal with capacitance? Remember our this one. And C is equal to QB. Alright? Can, right? Okay, so what I do is I assume a certain charge density, uniform charge density sigma on the surface of the metal. Okay, so now I have this one already. Now, then the next thing is that I draw a Gaussian surface here. I find the electric field. Now, Gauss' law, once again, E dot dA, because this is uniform, electric field is radially outward, and it will be constant at a certain distance r away, so this one equal to 4 pi r squared ER. Now, then it is equal to Q over epsilon. What is a Q? Q is a total charge enclosed. Total charge enclosed, it is equal to sigma times 4 pi A squared. Right? And divide by epsilon or epsilon naught. So my ER is equal to A squared over R squared sigma epsilon naught. Something like this. Right? Okay? If that is my electric field, what is my electric potential? V is equal to minus integral of E dot dl. Can you see that? Can you see that? This is the total charge enclosed. Charge density is sigma. Because this is constant, so the charge density multiplied by surface area, which is 4 pi a squared. Okay, so it's 4 pi a squared sigma divided by epsilon naught. So I have 4 pi r squared ER is equal to 4 pi a squared sigma. So I divide by 4 pi r squared over here. Alright, I divide my 4 pi r squared here and cancel with the 4 pi. Okay, that's it. Now, then this is equal to minus integral of sigma over epsilon naught a squared r squared dr, right, from a to b. A to b or b to a? A to b or b to a? From A to B, that means I assume that this is equal to BB minus BA because I integrate from A to B. Alright, so remember, that means I'm assuming that the potential at B is higher than A. Alright, but if it turns out negative, it's okay, right? That means the potential can be the other way around. Alright, no problem. So I just do my integration like this. After that, if it's negative, so be it, no big deal. So this is equal to sigma over epsilon naught a squared. Integrating r to the power minus 2 become r to the power minus 1, right? Let me see. Do I have to divide the minus 2? R minus 2 dr is equal to what? Is equal to r minus 1 over minus 2. Am I correct? Suddenly I forget my integrations already. Is it correct? Is it correct? Is it correct? Minus 1 only, This one only minus 1. Okay, If it's wrong, then it's your problem, Okay, so it's minus r minus 1 a to b, which is equal to sigma a squared over epsilon naught 1 over b minus 1 over a. Okay, so this is equal to sigma a squared epsilon naught ab a minus b. Is it correct? I don't know whether, whatever. Alright, so if so now you have determined the potential V, okay, then what you get is just capacitance is equal to Q over V. And what is Q? What is Q now? What is Q now? Q is equal to 4 pi a squared sigma, right? Q is equal to 4 pi a squared sigma. So Q over V. Okay, Q over V. Alright? Any questions? But this duster is so noisy, The board is so dirty. Okay? Now, next questions. As the break go, I don't think you can finish more paper. Okay, this is propagations, we leave it next week. This is propagations, we leave it next week. Okay. This one sounds difficult, long-winded, actually not. Okay, a student is conducting an experiment at an MRT station. Okay, now the MRT, right? He is measuring the voltage induced in the square loop due to changing magnetic field. Changing magnetic field, okay, changing magnetic field, that means there is a dV/dt over there. Arising from changing current drawn by the third rail, the power supply to the electric train. Okay, so this is the power supply to the electric train, drawn by the train. Why is very electric current? Because the current has to be changing, because the train is accelerating, decelerating, and all these things, so the current is changing. The square coil has sides of 10 cm and comprises of 5 turns. The coils is placed parallel to the platform. The geometry of the third rail platform coil are shown in figure 5A. Okay, so this is how does it look like. The geometry is redrawn as shown like this, with the third rail locating at the origin and point P at the center of the loop. The z-axis is out of the paper, so you can see that now it's like this. Now, so what? Ampere's law, right? You see one long straight wire and current. So now it's like this. This is the center with a current I. The coil is here. This is 1.5 meter up. This is 2 meter. And what is a magnetic field? Magnetic field, of course, will be like this, right? Am I correct? Ampere's law. Right? The magnetic field is go in that directions. Okay, so what do you want to find? For a current I flowing out of the paper, write down the magnetic field flux density at point P using Ampere's law. So at any point P, what is the magnetic field vector? At the point P, magnetic field vector H is equal to I over 2 pi r. And r is the shortest distance, okay, to the r. Okay, so this one, right marks, rule. Now, which component of the magnetic field has no effect on the induced voltage? Now, if I take a point P here, alright, take a point P here, the magnetic field will be like this. Am I correct? Because the magnetic field will be always tangential to this circle. When it's tangential to this circle, that means it is perpendicular to the radius. Alright, so this is like this. So which component of the magnetic field? Now this guy got two components. One component is like this, one component is like this, right? Okay, this guy is perpendicular to here, so it has component 1, vertical component, horizontal component. Which component of the magnetic field has no effect on the induced voltage? Obviously, this is X, this is Y, this is the Y component, this is the X component. Obviously, the X component will have no effect on the induced EMF, because if the plane is like that, the magnetic field like this, it never link, right? The magnetic field now has like this. Magnetic field is like this. So it resolves in two components. One is perpendicular, one is parallel. Now, this vertical component will link this surface. This parallel component never link. Okay, just like the CA, just slide across. So the component that has no effect is the X component. 3 marks. Alright, if I say that the X component has no effect, and that's 3 marks. Assuming that the magnetic field is approximately constant, assume that it is approximately constant, now you can multiply by the area. Okay, they give you the coverage over here now. They give you the say, hey, no, you can assume that constant, you can multiply. Write down in via Faraday's law the induced voltage due to current I. Alright. Okay. Now I call this angle phi. Okay? Now, h phi is equal to I over 2 pi r. Right? This is Ampere's law. Correct or not? Now, the horizontal x component has no effect, right? So we need the y component. Now, what is the y component? What is the y component? If this is angle phi, this is angle phi, this is angle phi, so the y component is cosine phi. So hy is equal to I cosine phi over 2 pi r. Now what is cosine phi? If this is 1.5, this is 2, cosine phi is equal to 2 over square root of 2 squared plus 1.5 squared, right? Correct, not? So this is cosine phi, but they never ask you to calculate, they just write down only. They never ask you to calculate for this, so don't calculate. If they never ask, don't do. Okay. Now, this is hy. So what is your Vy? Vy is equal to mu naught I over cosine phi over pi r. Right? And if they tell you that you can assume that it is approximately constant, so what is the area of the loop? So the flux is just equal to VA. You can multiply, alright, because they tell you you can assume to be constant. So it is equal to mu naught I cosine phi 2 pi r times A. This is flux. And what is Faraday's law? Faraday's law says that EMF is equal to minus d flux dt. So now it is equal to minus d dt. So finally, EMF is equal to minus mu naught cosine phi A 2 pi r. What is r? R is this distance, alright? R is equal to square root of 2 squared plus 1.5 squared, right? This is R. Okay? And di dt. Why di dt? Because the current, the question straight away tell you from the beginning, the changing magnetic field is due to the changing current. Alright, so the current is the one that is changing. Okay, there you are. That's 7 marks over there already. Okay, so that's 7 marks already. You don't have to calculate anything at this point yet. You can, they just ask you to write down the expression. So you just write down the expression. Okay, so finally, if the current changes like this, what is the induced EMF? And this is the same as the tutorial questions, okay? Tutorial question has the same something like that. So the di dt. Now, di dt around here is equal to 0. Okay, no gradient. Di dt is equal to what? This is 3000 minus 1000 is 2000. 2000 divided by 10 is 200. So it's minus 200. Di dt is minus 200. Di dt is equal to 0. Di dt is what? Di dt is again 2000 divided by 15 is I don't know what it is okay, it's a certain value, and then di dt is 0. So we just put that, put in all the di dt at the different time, you get the EMF at different time. And I said this is exactly the same as the tutorial questions. And this part is the one to actually to differentiate the good people. Last 5 marks, you have to be very good to do it. Not that it's very difficult, but that it is, you might not have time. Okay, so you have to do it very fast. Okay, that means you cannot assume this one. You cannot assume that this one to be the constant, so we cannot do E times A. So what must you do? So your B look at this one. This one is lying on the XZ plane, right? XZ plane. Alright, so that means your A now is dx dz. Okay, dx dz. Dx dz, but who? This is R. B is R. And cosine phi. And cosine phi is equal to 2 over R. Okay, so this is 2 over R squared. Okay, 2 over R squared. Right. Now, 2 over R squared. What is 2 over R? Okay, hang on. Not yet now. Because this is x now. Y is constant. On the loop here, the y is constant, but the x is not constant. Alright? So it's x over R. So it's x squared plus 1.5 squared x over R. So this is x over R squared. Okay, x over R squared, this is equal to x squared plus 1.5 squared. Okay, so now what you need to do is 5 is equal to b dx dz integrate, which is equal to mu naught I 2 pi x dx x squared plus 1.5 squared integrate dz. You have to do this integration. This integration is not difficult to do because you can substitute, right? You can. This one is not difficult to do because this is equal to mu naught I over 2 pi. I don't know, you can do the integrations. Okay. This one you can substitute. Let's say delta is equal to x squared plus 1.5 squared. So del squared. So 2 del d del is equal to 2x dx. Okay, so you can do the substitution, you can do the integration. But as I said, you have to be good, okay, in order to get the last 5 mark, because that is not simple. You know, can do it just off the shelf like this. Alright. So you see, assume constant is very much easier, but if you don't assume constant, it's not. Especially, why this one is especially difficult? Because every time this one is on this plane, this one is now elevated. Elevated, you have a cosine. And once you have a cosine, you've got this one comes in. Alright? So this is a bit more difficult to get the last 5 mark. Okay, any questions? Wow, 1 hour you only finish 1 paper. I think, not sure whether you can finish 3 papers or not. Any questions? Good. And it's a good size. I will actually worry about too many people and the room is not taken. But it's a good size. Okay, 2015. Charges are located in the space at P1, P2 with Cartesian coordinate. Wow. Okay, so it is not in the XY plane or YZ plane or anything, just like this. Okay. Origins O is 0. Point P3 is at Cartesian coordinate P1 minus 2. All distances are in meter. Find OP3 minus OP1. Okay, how to find? P1 is 1, 3 minus 1. P1 is 1, 3 minus 1. P2 is minus 3, 1 minus 2. P2 is minus 3, 1 minus 2. And P3 is 3, 1 minus 2. Okay, somebody tell me what is OP3 minus OP1? What is OP3? What is OP3? What is OP3? OP3 is 3x plus y minus 2z. Alright. Now what is OP1? OP1 is x plus 3y minus z. Okay. So OP3 minus OP1 is what? 2x minus 2y minus z. 2x minus 2y minus z. Alright. This minus this, 3x, 3 minus 1 is 2. 3 minus 1 is 2. 1 minus 3 is minus 2. Minus 2 minus 1 is minus 1. So 2x minus 2y minus z. Alright, no issue. OP3 minus OP2. Well, what is OP2? OP2 is equal to minus 3x plus y minus 2z. So OP3 minus OP2, 3 minus 3 is plus 6. 1 minus 1 is 0. Minus 2 minus 2 is equal to 0. So it's 6. 6. Alright? So, okay. Find the electric field E at point 3. Okay, electric field at point 3. How to find the electric field at point 3? I have P1 here, I have P2 here, I just anyhow mark, I have P3 here. Okay, I have P1, P2, P3, I just anyhow mark, okay? Not necessarily like this. Now, what is the electric field at point 3? I have a charge here, I have a charge here. If I have a charge here, that means my electric field is like this. Right? Is that like this? Right or not? Oh, okay. Sorry. Both charge, one is positive, one is negative. So if it's negative, am I correct? One is like this, one is like this. Now, what is the electric field? Q over 4 pi epsilon naught R squared A whatever. The unit vector that pointing from P1 to P2. Remember this one? Something like this. Okay? So now, what is the electric field at P3? Electric field at P3 comes from E1 minus E2. E1 is here, E2 is here. Alright, so what is E1? E1 is equal to Q1 4 pi epsilon naught. Now, what is this? What is this distance? What is this distance? What is that distance? P2, P3. What is this vector? What is this vector? OP, let's say 1. OP1 plus P1, P3 is equal to OP3. Am I correct? OP1 plus P1, P3 is equal to OP3. Right? So obviously P1, P3 is equal to OP3 minus OP1. Right? Okay? Now, OP3 minus OP1 is this one, right? Just now we said OP3 minus OP1. So OP3 minus OP1 is equal to 2x minus 2y minus z. Okay? So now r squared is equal to 2 squared plus 2 squared plus 1 squared. And the unit vector is equal to 2x minus 2y minus z divided by the magnitudes one more time, right? So this is 3 by 2. Sorry, 2 squared, small, so 5 by 2. Okay? Now, then the next one, this 6 mark is not easy, yeah? This 6 mark is not easy. So now, what is the other one? The other one is this one, E2. What is E2? E2 doing the same thing, alright? So E2 is equal to Q2 4 pi epsilon naught. Same thing, alright? Same thing. That is your 6x, right? So your P2, P3 is equal to 6x. Alright, so now this is 6, 5 by 2, oh sorry, no need, so it's just equal to 6 squared x. Okay. And then you do the thing sum up. Alright, so you do the same thing and then you finally get the solutions. Okay, this is a bit clumsy. Okay, because you got to do 2 times. Alright. 2 squared plus 4 plus 4 and 4, this is 9. 9 divided by 9 squared root 3 to the power of 5, so after you got to do 5. 3 to the power of 5, 9 times 9 is 81 times 3, 81 times 3, 1 should be 190. So there's something that can be cancelled, most likely 37, because there's a 3 down there. This is also a vector of 3. Either one of these, correct? Okay, then you just sum it out. Alright, so this one is a bit lecce, but you make use of this one, OP3 minus OP1 and OP3 minus OP2 to get the this vector. Alright, you get this vector, and then you substitute that in, and then after that you sum it up. So this one is a bit, this one, this is not easy, this is not easy. Alright. So you see that the two questions are set by the same person. Okay, 2015 is too difficult. So I think that we realize that the 2015 this question is too difficult. A lot of students got it wrong. The 2016 the same question is so much easier just now. Remember just now we saw.
I think both times were pretty difficult.
No, you see, once we realize that it's too difficult, the next one we said it's easier. But no problem because it's marked on the curve, right? You only got to be better than your friends sitting next to you. That's all. Yeah. Okay.
Thank you.
Any questions? Okay, this is almost the same. Okay, it's almost the same. Explain what it means. Okay. And I think it's probably because the same thing. These questions, the first time that appeared in 2015, a lot of students don't know how to do, never give answer, so it appeared in 2016 again. Hey, you guys, you got to look and pass your questions. If you don't do well, next time. So
last year which question they didn't do well? I got the hint, so last year which question they didn't do well?
Alright, so this one is almost the same also, right? This one is exactly the tutorial question. You recognize these two pictures. It's actually lifted up from the tutorial question. We cannot say that you don't know how to do it. Alright, so I'm not going to go through the tutorial questions. Plane wave. Okay. Another thing you see similar, almost every game of circle. So if you don't present a circle, that is your own problem. A sphere of radius A, never say it is vector. Enclosed by a spherical shell, it never say it's vector. So A, B, C. They have not said vector yet. Sphere from charge density, okay, if charge density is not vector anymore, rho r equal to 5r squared. Okay, 5r squared again, symmetry. Okay, E is equal to ER and all this, so your Gaussian survey can be done. Spherical shell has a total charge of 1 coulomb. Okay, that means this is also not conducting. Alright, none of this is conducting. You cannot assume conducting. Alright, for charge density cannot be conducting anymore, which is uniformly distributed over the shell. That means 1 coulomb is uniformly distributed. So what is the charge density? This rho v is equal to 5r squared. What is this rho v? This rho v is equal to 1 coulomb divided by volume, right? What is the volume? Volume is equal to 4 over 3 pi c cubed minus 4 over 3 pi v cubed. Can everybody see that? The volume is this particular volume minus this volume. Right? The volume of the shell is equal to the volume of the big sphere minus this volume. Right? Okay, huh? Okay, so this is the charge density over there. Uniform. Find the electric field in the following regions: R smaller than A, R greater than A, B, and so on and so forth. This is usual. Alright, remember now, for this kind of thing, first of all, straight away we say that, well, because of symmetry, electric field is always radially outward, and it is only a function of R. For any constant R, electric field is always constant. Alright, so if that's the case, now my E dot dA now is equal to 4 pi R squared ER. The only thing left is to find Q, charge enclosed. So for R smaller than A, what is the charge enclosed? The charge enclosed is equal to, which is equal to Q over epsilon naught. Q is equal to 5 R squared sine theta d phi dr. Right? Okay, so this is equal to 5r to the power of 4 dr integral 0 to r. 0 to r, not to a, alright? 0 to r because the radius of your Gaussian circle or Gaussian surface is r. Sine theta d theta 0 to I and 0 to 2 pi d phi. You see that this part is also standard. This part is also standard. Okay, every time you got sine theta d theta 0 to pi, this is 0 to 4 pi. This is also standard. So this one give you 2 and this one give you 2 pi, which is also standard. Alright, so you actually don't need to do anymore. This one 5 to R4 divide integrate, this one become R5 5 over 5 0 to R. So this is equal to 5 cancel 4 pi R to the power of 5. Alright. So now I got 4 pi R squared ER is equal to 4 pi R to the power of 5. So my ER is equal to R to the power of 3 over epsilon naught. Of course, don't forget my epsilon naught. Alright, so this is for R smaller than A. Now, what happens if I draw a Gaussian surface here? Draw a Gaussian surface here, then this side is still equal to 4 pi R squared ER. Now, what is the total charge enclosed? The total charge enclosed is by changing this one to A. So it is equal to A to the power of 5 4 pi A squared divided by epsilon naught. So ER is equal to A to the power of 5 over R squared epsilon naught. Right? Because when you draw a Gaussian surface here, you enclose all the charge inside here. You draw a Gaussian surface here, enclose all the charge inside here. So the integration, instead of integrating from 0 to A, 0 to R, you integrate from 0 to A, and then from here to here is 0 charge, right? Here to here is 0 charge, so integrate from 0 to A. Now, when I write like this, I might commit error, alright? So check for me. If there's error, let me know, alright? And I must put a caveat there, got error, don't blame me. Because when I write like this, I can get error. Sometimes the sign gets wrong, sometimes I forget about epsilon naught, sometimes, Okay, so finally, not yet. Wow, this is quite a tedious one also. Okay, so this year the question is not easy. Okay, 2015, 16 is not easy. Now, if you draw it here, this side is still the same, 4 pi r e, 4 pi r squared er is still the same, but what is the charge q? The charge q now has two components. One component is this one here. This one got no charge, and one component is this one here. Alright, so the first component q is equal, the first component is equal to what? Just now it's more than, it's 4 pi a5 over 4 pi a5, I will not explain not yet. So this is the first component. What is the second component down here? What is the charge enclosed in that blue shaded portion? Someone help me? Since it is constant, okay, constant, no need to integrate. Constant multiplied by volume. So what is the charge density? This is the charge density multiplied by volume. What is the volume? Volume between this one. You see, just now the volume is the big sphere minus the small sphere. So same thing, this volume is this sphere minus the small sphere. So now the volume is 4 over 3 pi r cubed minus 4 over 3 pi b cubed. So this is the component N to here. So that is the total charge. Charge density multiplied by volume. Can see? Everybody can see? Have I lost you? Okay. Now the charge has two components. One component is inside here, right? Okay, inside here is that's what is integrated down here, correct? Not this one integrated here, okay? So that one here. Now, then inside here got no charge, right? Okay, this is empty space, no charge. Then there's a charge inside this blue shaded region. Now, what is the blue shaded region? Blue shaded region, the charge density is constant. Okay, the charge density is constant, that means it's equal to charge density multiplied by the volume to give you the charge. Now, what is the volume of the shaded area? Just now we say that, well, what is the volume of this one? The volume of this shaded area is equal to this big sphere minus the volume of this small sphere, right? So same thing, we use the same deductions. The volume of this shaded area is the volume of this sphere, which is equal to 4 over 3 pi r cubed, minus the volume of this sphere, which is 4 over 3 pi b cubed. So then the volume multiplied by density is equal to charge. Alright, so there you go. A bit tedious, right? It's not that difficult, but it's a bit tedious. Alright? That's that 2015 is a bit difficult. 2016 is very easier. Or maybe we have dropped our standard every year. Maybe we have dropped the standard every year. Okay, so finally, when r greater than c, what do you get when r greater than c? R greater than c, this one is still the same. What is the total charge enclosed? Total charge enclosed will be including this one plus all of that inside, right? So it is equal to 4 pi a to the power of 5 plus 1. That's it. Because they tell you that the total, they tell you that the total charge inside this shell here, 1 coulomb, 1 coulomb. So since it is now outside, since now we draw a Gaussian surface outside, so the total charge is equal to 4 pi a5, which is this one, plus 1 coulomb. Okay, so now the then is get it. Alright? And I don't know, I mean, my printer or my Adobe, always give me this thing. I don't know what happened. When I convert it to Adobe PDF, I always give me this thing. Alright, no questions. Let's go down to magnetic field. Long straight wire. Hey, this one looks familiar. Long straight wire. Look familiar, the tutorial. Find the magnetic flux density. Oh, come on, that one is easy. First, X, Y. Okay, this is the current I here. So you are asked to find the magnetic field at the point P x0, 0. At any point here. It is simple, right? What is my magnetic flux density? V is equal to what? Mu naught I over 2 pi x, right? Because I is equal to x. Where is the magnetic field pointing? Where is the magnetic field pointing? If this is a current I like this, where is the magnetic field? The magnetic field going inside, right? Inside. X, Y, Z, so it is a minus Z directions. So it is equal to minus Z. Okay? 3 marks. Thus find the total flux linkage. Alright, total flux linkage to this one, not difficult. Alright, total flux linkage. So flux linkage phi is equal to d phi is equal to dx dy. Alright, and this is negative positive because the area is doesn't matter, or you take care of it yourself. Okay, dx dy because dA is supposed to be dx dy z. So the dot becomes minus. So this is equal to minus mu naught I 2 pi x dx dy. Alright. So the flux linkage, total flux linkage is equal to integral of mu naught I 2 pi x dx dy, integrate from here to here, from here to here, right? That is equal to x is from where to where? Did they give the value? Oh, x to x, okay. Which is x equal to big X to big X plus S. Y is equal to minus L by 2 to L by 2. Alright, but that integration is not difficult to do. Okay, so you can do the integrations. The next so they give you 3 marks, they give you 8 marks, 11 marks. So at least you got some base mark already. The next one is a bit difficult. The metal loop is now being pulled along the xy plane. Then velocity v0, which is equal to dx dt, phi by Faraday's law, the EMF views, and say that it's whether clockwise or anti-clockwise. Now this guy is being integrations, it is now in the functions of big X, right? Okay, after integrating, you substitute with that, this is a function of big X. Okay, it's a function of big X. Now, if from Faraday's law, EMF is equal to minus d phi dt. Alright, so in this one, if this is, I'll just write it down, okay? So it is equal to minus L mu naught I 2 pi x plus s minus log x plus s minus log. Am I correct? Something like that, huh? Okay, integrate with respect to y, so become minus L by 2 become L, and then 1 over x becomes log x, so it's something like this. Okay? So this is phi. Now you have to differentiate with respect to t. Now, differentiate this one with respect to t, then what you get is mu naught I L 2 pi d dt log x plus s minus d dt log x. Right? Differentiate with respect to t, and there's a minus sign there, so we can minus sign like this. Now, do you know how to differentiate with respect to log? Can, right? You know how to do log? Integrate 1 over r become log. So differentiate log become 1 over r. Right? Correct or not? So this one become equal to minus mu naught I L 2 pi x plus s dx dt minus x dx dt. Right? Okay, and what is dx dt? Dx dt is equal to mu naught. Dx dt is equal to mu naught. Okay, so you just substitute mu naught inside there, you get your induced EMF. Alright, so those are not difficult actually, no? But it's a bit lengthy. Now finally, is it clockwise or anti-clockwise, the induced EMF? Can somebody tell me? The magnetic field is going inward. Alright, and when it pulls away, is the magnetic field getting stronger or weaker? Weaker. Okay. If going to weaker, that means the Faraday's law must generate a current which gives you the magnetic field in the same directions, so that to make sure that it don't weaken so fast, right? Okay, how to get the magnetic field in the same direction? So it is this way, or is it this way? This way, right? So the induced EMF is clockwise to actually supplement the magnetic field. Alright, so there you go. The last two parts is a bit difficult. Okay, the first three parts are quite simple. The last two parts are a bit difficult. Can you do this? X equal to QB cross B. Now, what does it mean? The last part. F is equal to QB cross B. Now the B side. Alright? The thing is going inside. Now, when this thing is being pulled, okay, when this thing is being pulled, where is the velocity? The velocity of Q is in that direction. But in that direction, electron in that direction. Velocity of Q is in that direction. Okay, velocity of positive charge in that direction, because velocity of electric charge, electrons is in that direction. Velocity of positive charge in that direction. So Q over V. Q over V. Now, in this line, Q over V, that means the force is downward. If the force is downward, doesn't mean anything. Okay, doesn't mean anything because it never push, never do anything. This one, same thing. But when this one here, Q over V, the force is downward, that means you are pushing the charge to be accumulated on this side. Okay, you are pushing the charge from here to accumulate here. Same thing for this one, you are pushing the charge to accumulate here. Alright, so there are some positive charge accumulated here, and there are some positive charge accumulated here. But these two lengths, no effect. Now, but these two lengths where got effect, F equal to Q V cross B. But the B at this point and the B at this point are not the same, right? Okay, so this guy will accumulate more charge than here, because the B is stronger than this one. Alright, now, so this potential, there is a potential plus and minus here, V1, there's a potential plus and minus V2. So what is the induced EMF? The induced EMF is equal to V1 minus V2. Alright, and you have to prove that V1 minus V2 is equal to the same as you get it from the Faraday law. That concept is a bit difficult. Alright,
I don't think you got
if F equal to QB, it moves the charge into two extremes. But because the B are different, although the QB, the velocity is the same, because they are same loop, same velocity. Velocity is the same, but because the B is different, so different B will give you different F. So the different charge accumulation. Different charge accumulation means that the V1 and V2 not the same, V1 and V2 the same, that means a current will flow, because the same loop, they get different potential, so there is always a difference, right? V1 and V2 not the same, so the current will start to flow. Okay? So then you have to prove it. So if this is plus and minus, so the plus and minus will drive the current this way, it will drive the current this way, but this is stronger than this one, so the current will drive this way. Okay, so there's the end of it. 2015. Wow, I don't know whether I have to do. Sorry? Same way lah. It have to be same way as the Faraday's law. If it's different from Faraday's law, then it's wrong already. Okay. Now let's see whether we can quickly go to 2014 or not. Or those, which is the least important one. one I think is quite simple. Alright. The charge is at 2, 2 and the electric field at 5 minus 2. The charge at 2, 2, you apply electric field P at 5 minus 2. So basically it's like this, right? Okay, so electric field now is equal to Q, which is equal to 500 pi epsilon naught, 500 pi epsilon naught, which is equal to 4 pi epsilon naught. What is this length? Five 2 and 5 minus 2. So what is this length? The difference is 3, 4, right? So it's actually equal to 3 squared plus 4 squared. Am I correct? From 2, 2 to 5, 5 minus 2. 5 minus 2. This is 3, this is 4. Right? 2, 2 to 5 minus 2. Am I right? Yeah, 2, 2 to 5 minus 2. So, you can see that 2, 2 is here. 5 minus 2 is xy coordinate. Reverse. I beg your pardon. Huh? Sorry. So, x, y, 2, 2, and 5 minus 2. Okay, 5 minus 2. So this is this is 4. This is 3. Right? 2, 2, 5 minus 2. This is x equal to 2, this is x equal to 5, this is y equal to 2, this is y equal to minus 2. Alright? So it's still the same 4 and 3. And 3 squared plus 4 squared equal to 5 squared, this is 25. So this is 25. And the unit vector is equal to down below. So the unit vector is equal to minus 3x minus 4y divided by 5. Okay, so this is a very simple question. In fact, I don't know why it is one here so simple, one here so difficult. This is very simple, right? Okay. In this below, this is also tutorial questions. A circular loop of A equal to 10 cm situated within a uniform magnetic field. Okay. H equal to H naught pointing into the paper when H naught is equal to this, B equal to mu naught. And on this one, the amplitude will reduce CMF. This is just actually direct applications, alright? Because the magnetic field constant flux is equal to magnetic field multiplied by area. Okay, constant means it's not constant with respect to time, alright? Constant with respect to locations. So it's just equal to magnetic field multiplied by area, which is equal to pi a squared. And then the induced EMF is just equal to minus d by dt. Alright, so that is easy. Direction is also easy. Alright, this is also because it's a cos, it's a cosine. Okay, cosine, that means the magnetic field is decreasing, right? After t equal to 0, after t greater than 0, magnetic field is decreasing. If the magnetic field is decreasing, that means once again the induced EMF must be in that direction so that to reduce the decrease. Alright, so this is quite simple. So this here is quite simple. me to go through, finish it? Is it okay if I overshoot the time?
Okay.
Okay, yeah? Not going for anything, huh? Alright, a point charge, 1 equal columns here. The charge shell has a charge rho R, V equal to 4R. Okay, simple. Indeed. 1. Rho V. Now, so this one, as usual, assume, no, since it's symmetry, radially outward, it's constant, and all these things, blah, 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 blah. Okay? So, Q over epsilon naught. Now, when I draw this, ask A or B? A and B, okay, this is A, this is B. R smaller than A, Q is equal to 1. Right? This one Q equals 1 colon, 1 colon, right? Okay. When R is greater than A, smaller than B, standard, very standard. Rho V R squared sine theta d phi dr. Come on, so standard. And what is a rho V? For R. So now Q is equal to 4R R squared sine theta d phi dr, which is equal to 4R cubed dr, integrate from 0 to R, 0 to pi sine theta d theta d phi 0 to 2 pi. This one give you 2 pi, this one give you 2. Again, so standard. Alright, again, so standard. And this one is become R cube R4, this one become R4. So this is equal to 4 pi R4. So 4 pi R squared ER is equal to 4 pi R4 epsilon naught. So ER is equal to R squared over epsilon naught. Okay, that is from here to here. Sorry, oh, plus 1, thank you. Plus 1. Plus 1. Yeah, thank you, plus 1. Okay, plus 1. So it is not just like this. So it is equal to 4 pi R4 plus 1 over 4 pi. Alright. Yeah, finally it is a whole thing. What is a whole thing? It's a whole thing, that means this is 4 pi what? Hey, I'm sorry, huh? Because this thing is integrating from here to here, okay, from here to, not from 0. I just write 0, which is wrong. Okay, I write 0 is wrong. From here to here. So it is from A to R. A to R, alright? So A to R, so this is equal to R4 minus A4 pi. Alright, I beg your pardon. Okay, so you got to put that in here. R4 minus A4 pi plus 1. Okay, and then you get largest is from A to here, not from 0. Alright, I beg your pardon. Huh? And finally, when it is outside here, it is very simple, right? You change R4 to B4. And that's it. Okay? Alright. Any questions? Any questions? Everybody? Okay. This one. Wow, this is so much long, eh?
So this question come out, I won't do.
Sorry?
This question come out, I won't do.
You won't do ah? You will choose the other two, yeah? Because you can only choose one. Now, actually not that difficult. Although it said 4 length, but did you notice or not? Did you notice or not that the current comes like this? This magnetic field go this way. This magnetic field, that magnetic field. What will do? The horizontal of the magnetic field actually cancel off. If you look at the if you look at this one here, the point P is here. There's a current, Alright? There's a current. Okay? The magnetic field at this point, you remember your Bell-Savart law? If your ds is here, the mu r is here, where is your magnetic field that is going to be? If this is your ds, this is a ur. ds cross ur, what do you get? This guy, so that means the two horizontal components cancel off. Same thing if you look at these two here, the two horizontal components also cancel off. So what is left is actually, you do it once only, because 1 is equal to 4 times. You see, the horizontal component cancel off, but the vertical component add up. So the same thing, these two will have the horizontal component cancel off, vertical component add up. So you just do it once. And the vertical component multiplied by 4 times. And how to do this one once? It is in the lecture note. Remember exactly the same as lecture note, that the one straight line here, minus L by 2 to L by 2. Can you remember? Cannot remember. So don't say don't do too soon lah. Exactly this one. Minus L by 2 to L by 2 in the center. So it is exactly this one. You just multiply by 4 times. So although it looks difficult, but it's not that. If you recognize the symmetry. Okay? But of course, if my point P is outside the origin, outside this line, outside the z-axis, then cannot, no cancellations. Okay? Anything else, ladies and gentlemen? If not, I will see you Tuesday. We will continue with the transmission line and hopefully we can finish off the transmission line. Alright, thank you for coming.